In order to use Newton's laws, you're going to need to know what forces to look for in a given system. This is our catalog of forces, the common forces that we're going to see most often and that we're going to look for in systems. The first force is the weight. Weight is from Earth's gravitational field, and weight in particular is the special case when you are close to Earth's surface. So we're using the same model that we would use for free fall. The object's weight is constant for a given value, for a given object near the Earth's surface, and it always points straight down. The equation for that is mg is the magnitude of the weight. Tension is the force carried by a rope or string or cable or wire. The tension always pulls towards the center of the rope from the end. So if you have an object, two objects that are connected by a rope, that rope pulls both of them in the direction towards the middle. Notice that there's no equation for tension. It is a reaction force. So however hard you're pulling on the two objects, tension is going to pull back so that that rope doesn't break. When we're looking at tension, usually we're assuming that there's no elasticity here, that these are inelastic objects, meaning that they're not going to stretch. A spring force is a special case of tension. It's a special case where the object will stretch or compress. And the equation is negative kx, where k is the spring constant related to the elasticity of the object, and x is how far it is stretched or compressed. We're not going to deal with this right now. We're going to see this in a later module. The next force is the normal force. The normal force is a lowercase n, has to be lowercase n because capital N is already the symbol for newtons. We get a normal force whenever an object is pushed against a solid surface, and the normal force acts perpendicularly outward from that surface. There's no equation for normal force because it is also a reaction force. However hard you push against the surface is going to push back with the equal force up to its fracture point. The apparent weight is our perception of our weight, and our apparent weight is found by the normal force. When you feel your weight, you feel really the normal force of the ground pushing on your feet. You don't feel your own actual weight. We have two different types of friction. Static friction is for stationary objects. Kinetic friction, think of kinesiology or kinematics. Kinetic friction is for an object that is in motion. For static friction, it's a force that is parallel to the interface between two surfaces. The force of static friction points against the direction that the object would move if it were not for the friction holding the object in place. And static friction is a little bit complicated because it is a reaction force up to a maximum value. The actual force of static friction is less than or equal to some maximum static friction. So if you don't push on the object at all, there's zero static friction. If you push on the object a little bit, there's a little bit of static friction holding you in place. If you push harder, there's a little bit more static friction up to this maximum value. And once you push harder than the maximum static friction can resist, then the object will start to slide across the surface. The equation here is mu times n, where mu s is the coefficient of static friction, and n is the magnitude of the normal force. This same equation, the same expression we see for kinetic friction as well. The difference here is that this is the maximum static friction, and the actual static friction at any instant is less than or equal to this maximum value. Once the object is in motion, and you have the object sliding relative to the surface, then you have a constant kinetic friction, and this is the equation for the magnitude of the constant kinetic friction. This is the coefficient of kinetic friction, and again, the magnitude of the normal force. The kinetic friction has this magnitude. Its direction points against the relative motion between the surfaces, and again, it is a constant value for a given system. Drag is also is another similar type of force. Drag is when you are moving relative to a medium, like a fluid, like gas, like air or water. And drag points against the direction of relative motion. So if you're trying to push through air or push through water, drag pushes you backwards. It depends on the speed and size of the object and the density of the medium. The equation that we're going to look at for drag through air is going to be 1/2 times c is our drag coefficient. That is a measure of the aerodynamics of the object. This is a rho. Rho is the density of the gas that we're pushing through. A is the cross-sectional area of the object. a larger object has to punch a larger hole through the air, and so you'll have more drag there, and v is the velocity of the object as it travels. We're only going to use drag for very large objects that are moving fast. Whenever we have a v² term here, that's going to give us a nonlinear equation that ends up being very difficult to solve, and that's why we're going to avoid including drag whenever possible. Our thrust force is a force from a rocket motor or a jet engine or a propeller. These are all very complicated machines, and our thrust is just a simplified approximation. We're going to assume a constant value being provided by this rocket motor or jet engine. So this is something that would be given or that we would find. It's not something that you would be expected to know. And lastly, our general force is a catch-all term for any other forces that don't quite fit. So for example, if a person is pushing or pulling on an object, if a person is holding an object up with their hand, we can just use a general force to represent the effect of that in our system. This is something else that must be given or found. There's no equation for this.